Good morning, everyone again. I am Tamás Csapó, and I will be the session chair for the Articulation and Naturalness. Our first speaker will be Debasish Mohapatra from the University of British Columbia, Canada, and his talk is about vocal tract area function extraction using ultrasound for articulatory speech synthesis. So please give your presentation.
Thank you. Good morning. Thanks for being here for my presentation. We are trying to explore the possibility of extracting vocal tract area function using ultrasound, which can eventually help us driving an articulatory speech synthesizer. So today I'll be mainly discussing about why are we working toward area function-based speech synthesizer and how the ultrasound imaging modality can be an option for extracting the vocal tract cross-sectional areas. The existing state-of-the-art speech synthesis models record human voice directly or use various visual cues such as video recording and imaging modality to capture the articulatory movements such as lip and jaw position, shape of the tongue, etc. And then using a deep learning-based algorithm, these models extract several acoustic, linguistic, and articulatory features from the recorded information. Then they map these extracted features to an acoustic space and produce synthesized speech output. So the efficiency of this speech synthesis model mostly rely upon the size of the recorded audio and visual data, which require a certain amount of memory space. Alternatively, the area function-based articulatory speech synthesizer does not require any prior information of individual articulators or the recorded audio to produce synthesized speech. It only depends upon the geometry of the upper airway, which is a set of cross-sectional areas to produce simulated speech output. That's why we are focused towards area function-based articulatory models. The articulatory speech synthesizer emulates the speech production mechanism through computational model of speech anatomy. It consists of three components. First, the trachea system, which allows continuous airflow from lungs to the glottal system. Then the glottal system, which contains the self-oscillatory vocal folds. The vocal fold periodically vibrates to convert the continuous airflow into acoustic energy or the acoustic waves. And these acoustic waves pass through vocal tract, which constantly deforms as we speak and acts like a filter or modulator to generate speech-like sound. Today, we will be focusing only on vocal tract modeling using ultrasound imaging. In literature, multiple imaging modalities have been adopted to capture vocal tract and extract its corresponding area function. For example, earlier we used X-ray to image complete vocal tract. However, it has the radiation risk to the subject being imaged. Currently, we mostly use MRI and in some cases, CT scan to track the vocal tract movements. The MRI has the potential to produce high quality images for the static vocal tracts. However, its spatial resolution decreases in case of dynamic vocal tract as we use the real-time MRI or RT-MRI. Moreover, the image acquisition time is very high using these methods. Alternatively, we can image the static and dynamic vocal tracts in real time at a higher spatiotemporal resolution using ultrasound. And it does not have the radiation risk to the human subject, but the downside of ultrasound is it does not capture the complete upper airway. Rather, it only images movements of the tongue blade, which is an essential part of the vocal tract. The key motivations of our research are, we can use this method to image the vocal tract and build a model for clinical research, such as studying post-surgical impacts, or understanding the process of learning new languages through vocal tract imaging and modeling. And it can also be useful in designing the speaker-specific articulatory speech synthesizer or silent speech interfaces. So the objective of our research is exploring the feasibility of extracting cross-sectional areas of the upper vocal tract using ultrasound to drive an articulatory model and synthesize speech sounds. For our experiment, we selected a 26-year-old non-native English male speaker. We used the Eloka SST 5000 ultrasound system and a 3.5 megahertz convex ultrasound transducer to image the vocal tract movements. During the ultrasound imaging, we asked the subject to speak 4 English vowel sounds as highlighted here. We have primarily selected these vowel sounds as they have simple vocal tract shapes, as well as they are the cardinal vowels representing the extreme point of articulation. In this work, we have only analyzed the static vocal tracts because we wanted to make sure first that our method works for simple vocal tract geometry before investigating the complex shapes such as dynamic vocal tract or diphthong sounds. Moreover, the vocal tract shapes of these vowel sounds are already been studied and their acoustic properties have been characterized using various vocal tract models in literature. For data collection, first we asked the participant to repeat each vowel sound 5 times. To make a clear distinction between each repetition, we provided a resting time interval of 10 seconds. During the experiment, the ultrasound transducer was placed under the speaker's chin at a fixed position. To avoid any unwanted head movements which could distort the tongue and palate position, we supported the speaker's head with a supporting pad. To estimate vocal tract contour area function, we need to image both the tongue and the upper palate. Ultrasound provides a higher spatial resolution of tongue movements. However, due to the air gap between palate and the tongue blade, there is no straightforward way to image the upper palate, which is the upper boundary of the vocal tract. Therefore, during imaging, we asked the participant to make a swallowing action, which in turn closes that gap and allows the imaging of the upper palate. Then we used the H-track, a semi-automation tool, to trace the palate and tongue position by fitting a smooth spline to the lower edge of the visual lingual contours. For a comparative study, we also recorded the speaker's audio and extracted the first 4 formats. So here is a hand-drawn example of how we derived the vocal tract center line and thus corresponding area functions. First, we superimpose the traced contours on a 2D Cartesian coordinate system and sample the coordinates for both the tongue and upper palate. To derive this center line, we average the coordinates of the tongue palate corresponding to each abscissa in the set of sample points. And from there, we derived a set of middle point coordinates between the vocal tract contours. By connecting those middle points using piecewise line segment, we determine the center line. To extract the vocal tract area function, we drew a set of equidistant grid lines perpendicular to the center line. Each grid line intercepts the posterior superior palate contour and the anterior inferior tongue contour. Then we calculated the cross-sectional area of the vocal tract tube from the length of the intercepts at the sampled points. Using the area function, we then built our vocal tract model using the finite difference time domain scheme. First, we created the rectangular grid, also known as the Y grid, inside the simulation domain. And then for each grid cell, we define whether it is the vocal tract wall or the boundary cell, or it is the air cells. Then for each grid cell, we define the acoustic parameters such as pressure and velocity, as well as the geometrical components which has been derived from the area function, that is the vocal tract depth. During the simulation, we applied the Dirichlet boundary condition at the mouth end, which means the current implementation of our model does not capture energy losses due to the mouth radiation. A virtual microphone was placed 3 mm inside the mouth to register the outgoing pressure waves. An impulse velocity pulse was added at the tube starting point as the source excitation and to investigate the frequency response of the model. Since ultrasound may involve the unwanted movements of the speaker while uttering speech, we first studied the reliability of this approach for area function extraction. To do so, we first matched the spectral envelope of vowel A over multiple utterances. As you can see here, the peaks of the frequency response curves for different trials are almost identical, confirming the format frequencies are the same. Next, we compared the extracted formats of our speech synthesizer model with the recorded speech signal from the subject for all 4 vowel sounds. Here we analyzed only the first 4 lower formants as they play major role in determining the vowel sounds. As you can see here, in most cases, the absolute percentage of the accuracy of the formants for vowel A and A are greater than 80%, but still far away from a complete satisfactory results. The mismatch in the format frequencies between synthesized and recorded speech can be contributed due to a couple of factors. The first one is like our speech synthesis model does not consider the mouth radiation. Second, ultrasound can only image a part of the upper airway. We found a greater mismatch in case of vowel E and O, as vowel O involves the extension of the vocal tract by lip protrusion. The ultrasound image does not produce precise formats. Therefore, we need to incorporate some of the assisting technologies such as external sensors to estimate the shape of the complete vocal tract. And then only we can get a precise format position for the lower formats. In terms of future plan, we are planning to implement the mouth radiation for more objective analysis so that we can correctly compare both the synthesized output as well as formats extracted from the recorded speech signal. And we also need a complete vocal tract imaging. So in addition to the ultrasound imaging, we have to add some other external sensor which can give us a complete accurate geometry of the lips as well as the lower vocal tract. And the method should be tested for more complex vocal tract structure, such as like dynamic boundary and diphthong sounds. Thank you.
Thank you very much for the presentation. And I see that we have a question online from Paul. So I have a couple of questions. So first of all, I have seen that you are using ultrasound, two-dimensional ultrasound, and you mentioned that it's beneficial compared to the MRI. And I wonder, like, could be three-dimensional ultrasound used for this purpose?
Yeah, definitely. Like right now in our lab, we did not have that 3D ultrasound, but I think like if we'll go for the 3D ultrasound, that will give a very clear picture of the whole vocal, the whole tongue and the palate position, all those stuff. And at the same time, I don't think only 3D ultrasound will be enough, because you can see like ultrasound is only capturing the tongue blade, but it is missing the lip position and the like from the vocal fold, the lower vocal tract position, it's missing those geometries. So I need to track those geometries as well. Then if I get the clear picture of the whole vocal tract, then our speech synthesis model can create a very precise formats.
Okay, thank you. Do we have questions from the local audience? Meanwhile, I have a second question that at the end of the presentation, you mentioned this formant mismatch. And I wonder that you mentioned that the tongue tracings were done with edge track. So yeah, is it possible that maybe the tongue contours are not, I don't know, fully perfect, and this might be related to the formant mismatches?
Yes, yeah, that's a good question. Like that could be a possible reason, but the thing is, what we need to check in our future work is like if there is a, let's say, if there is a distortion in terms of while collecting the data, how much it is like how much it is contributing to that error factor. Here I showed, we did one thing, like we collected the same tongue blade. We imaged the same tongue blade again and again, like for 3 to 4 times. And we, in one graph, I showed like how the spectral envelope is coming. It looks like they are same. So from that, I can say, okay, I mean, it's almost identical at each trial for in the data collection. But we need to check, like the way you ask, like how much that contributes to the error factor.
Okay, thank you. I have a last question that, so in this study, you were using only the static cardinal vowels. So I wonder how difficult it will be to go to, I don't know, words or continuous speech or diphthongs. So I don't know, can these things be used automatically, or what is the next steps towards longer speech?
Yeah. Okay, so here in my work, there are two things. Like first part is imaging, the ultrasound imaging, and the second one is like using that data in the speech synthesis. So when it comes to complex focal tract geometries like continuous sound, speech, or word, the more difficult thing comes in the speech synthesis designing part, because we have to model the speech synthesis in such a way like the boundary will continuously change inside the let's say finite difference scheme, the method I am using to solve the acoustic solver. So that's where the difficulty may come, but it has already been demonstrated in 3D, like for diphthong sound, vowel to vowel transition. So it's possible. It's not like it's not possible. It's definitely possible. But another factor is like what's the simulation time it will take, because that's so when we go for articulatory speech synthesis, how much simulation time it will take. So that's is another factor we have to check.
So I have another question.
Yeah.
How many tube sections did you use, and did you study the effect of the number of tube sections?
20. It's around like 25 to 26.
Okay, but did you vary them? Did you try that
out? Yes. Yeah, that's a good thing. I mean, for a more accurate focal tract geometry, we should go for more tube sections. But in this work we have not varied that thing. It is fixed like 26, I think.
Okay.
Okay, so thank you very much for your presentation again.
Yeah, thank you.
The next presentation will be given by Raahil Shah from Amazon, and the topic is non-autoregressive TTS with explicit duration modeling for low resource, highly expressive speech.
Yes, I'm just setting up the presentation. Great. Apologies for the delay. Let me start the presentation now. So, hi everyone. I'm Raahil Shah. I'm presenting for non-autoregressive text-to-speech with explicit duration modeling for low-resource, highly expressive text-to-speech. I work for Amazon Text-to-Speech Research in Cambridge in the UK, and this is our presentation on the topic of data reduction for highly expressive voices, to put it more simply. Quick overview of the presentation. So basically the topics we'll cover is a bit of background on the problem statement, what we are trying to solve and why that is important. A little bit into our approach. So we'll dive deep into the 3 steps of our proposed approach and the technologies that we use, the changes that we introduce. Then we'll look at some results that we get, including some ablation studies for some of our proposed architectural changes, and then the conclusions we can draw from that and steps into the future. So let's start with the introduction. What is data reduction? Simply put, it is the problem of trying to synthesizing high quality text-to-speech voices with as little recording data as possible. Why is this an important problem? Well, that's because data collection for text-to-speech, as many of you might be familiar with, is a time and effort consuming process. It can be very expensive, requires a voice talent to sit for hours in a recording studio, and the cost of that scales with the amount of data that we need to record, as well as how expensive the voice talent is, which can get very expensive in the case of a celebrity. So lowering the cost of that and doing more with less is a very valuable proposition for text-to-speech research. Where do we stand in terms of low resource text-to-speech? So what is the state of the art currently in the field of data reduction for text-to-speech? Well, Our previous work published last year at ICASP introduced a 3-step methodology to perform low resource text-to-speech, where using as little as 30 minutes of data from the target speaker, we are able to synthesize high quality target speech that is on par with speech that is on par synthesized from roughly 10 hours of training data, which is standard for the current state of the art in text-to-speech models. And this 3-step approach basically addresses the limitations of the low resource constraint, that is the lack of target speaker data we have, by using data augmentation. So we create synthetic data using a technique known as voice conversion, which many of you might be familiar with, to address some of the lack of target speaker data that we have. We also combine the training data when training our text-to-speech models with data from other readily available speakers by training multi-speaker text-to-speech models. And lastly, we perform some domain adaptation to fine-tune this for our target speaker. So this 3-step approach is what we introduced in previous work as the state-of-the-art in data reduction. And with that, we're able to achieve about 80% in naturalness and speaker similarity relative to recordings. So an 80% ratio of Mushra scores relative to recordings for most of the voices that we evaluated in that work. So that was 7 out of 10 of the conversational voices that we evaluated in our previous work. That begs the question, what about the other 3 voices? So we analyzed the data from our previous experiments to understand the limitations of the technology that we were proposing. As we see, the other 3 voices were performed slightly under par, achieving about 73% naturalness relative to recordings. And to understand why that is, we dove a bit deep into this data and found that, in fact, these voices were challenging because they were more expressive. That is, outliers in this heuristic of expressivity, which we've had many discussions on at this conference. But what we measure expressivity to be in terms of was in terms of dynamics on acoustic features. So we measured the mean and variance of frequency, energy, and phoneme duration features, as well as their derivatives or changes in time through an utterance. And these are features that we use to analyze the expressivity heuristic. And we found that these 3 voices were more challenging because they were more expressive than the other 7 where we performed well. So we decided to tackle and address this limitation with data reduction, is to see how can we do more with less for even more challenging voices that are as expressive as they can be. And for this work, we challenge ourselves by picking the most expressive voice that we have. So that is even more expressive than these 3 voices that we had room for improvement on. And we pick up to, we investigate different data amounts up to 3 hours of data for this target speaker, who is the most expressive voice in our catalog. Unfortunately, this is the voice of a celebrity. So due to business confidentiality reasons, we won't be able to share samples of this voice through this presentation. So let's quickly dive deep into our approach and the proposed architectural changes. So the first step of our approach involves augmenting the low resource target speaker that we have with synthetic data that we produce using voice conversion. So the voice conversion step is largely similar to that in our previous work. We use a voice conversion architecture that is a copycat prosody transfer model that we introduced and published from Amazon a few years back. At a high level, what this model does is it converts data from a readily available source speaker to sound as if it were coming from our target speaker. And it does this by, during training, trying to factorize out the speaker identity of the source speaker from the acoustic and phonetic content. And so at inference time, when we provide the identity of the target speaker, the speaker that we care about, we are able to convert any source audio, that is the spectrogram, into audio from the target speaker. And we use this technique to generate about 4.5 hours of synthetic data for our target speaker to bolster the 15 minutes to 3 hours of data that we will use as ground truth data. And the only difference between this and our previous work in terms of architectural changes for voice conversion is we find that in the case of these the more expressive voice, fine-tuning the copycat model, that is training the model on target data just after the baseline training for about 50,000 steps, did lead to improved quality of converted samples. So once we have, now we have this target speaker data in a limited amount, we have some synthetic data to bolster that low resource data. We are ready to start training to some text-to-speech models and get some speech, which we do using multi-speaker text-to-speech architectures. So, and the reason we choose multi-speaker models is once again to address the low resource constraint. We have data from readily available speakers and we combine them using multi-speaker architectures to try to synthesize quality speech for a low resource speaker. So we train an acoustic and a duration model. This is a part of our proposed architectural changes. So the state of the art that we improve on is largely based on the Tachytron 2 based architecture, which uses attention to align the phonetic and acoustic sequences. We propose that to tackle more and more expressive voices, modeling duration separately is a better approach, and we investigate that in this work. So our architecture improves on the baseline by introducing a non-autoregressive acoustic model and modeling duration separately in an external duration model. And this is in line with the latest state-of-the-art text-to-speech architectures. So what is the same about the baseline acoustic model? Things that we're familiar with, the use of a reference encoder that is a variational autoencoder to encode residual information from the reference mel spectrogram, phoneme encoder based on Tachytron 2. For speaker to encode speaker identity, we use speaker embeddings from a pre-trained speaker verification model. And lastly, we have this one hot flag to indicate whether the data is real or synthetic data that we produced using data augmentation. What are we changing? Well, in this non-autoregressive external duration modeling world, we introduce a parallel decoder that is key to the non-autoregressive architecture based largely and only on convolutions. We also introduced this explicit duration model, which is trained separately. And so at training time for the acoustic model, we perform teacher forcing for durations using the oracle durations that we have extracted using forced alignment. And only at inference time do we use the durations predicted by our external duration model. To bolster this alignment information, we also provide the decoder with additional positional embeddings that one might have seen in transformer-based architectures that encode information like the phoneme duration as well as the position of a frame within a phoneme and pass this information on to the decoder. For our duration model, it's fairly simple. It is based on a Tachytron 2 phoneme encoder conditioned with the pre-trained speaker embeddings to provide speaker identity, so also trained in a multi-speaker setting, and uses an L2 loss on the log domain of the durations. Finally, we introduce for the third step, we introduce an additional new technique that is fine-tuning using conditional GANs. So in our previous work, we fine-tune our acoustic model by training only on the target speaker data at the end of multi-speaker training. We introduce here a new technique using GANs, where we add a discriminator network to try to discriminate between the real and fake samples produced for our target speaker. And we use the self-attention GAN-based discriminator architecture for this GAN. We also introduce a trick to condition the discriminator on the phonetic content. And we hypothesize that this helps to distinguish between real and fake samples even better, leading to improved adversarial training. So let's look at what these approaches give us in terms of results. We will look into two different studies. One is an ablation study for the conditional GAN fine-tuning technique that I just spoke about. And as we can see here, compared to our baseline with just vanilla fine-tuning, so no GANs applied, as well as a baseline, as well as our multi-speaker model fine-tuned with the standard GAN network, we find that adding the phoneme conditioned GAN brings a statistically significant improvement to our multi-speaker fine-tuned synthesis. And as our main study, we investigate this final proposed system that is our data reduction system using the 3-step data reduction methodology, along with the no attention architecture, that is the non-autoregressive external duration model based architecture, as well as condition GAN fine tuning. So all of our improvements as our candidate system. We compare this to a few different baselines. So the baseline using the same architecture, but without fine tuning, so as to understand the efficacy of the fine tuning step using conditional GANs. We compare this to a data reduction baseline using our previous architecture to understand the impact of our architectural changes. So that is based on a tachytron 2 based attention architecture. And finally, we also have some anchor systems trained on full data, that is 10 hours of data for the target speaker. One uses the no attention architecture that we introduced. So just to understand the difference in the improvements brought about by our data reduction methodology. And lastly, a full data single speaker system trained only using the attention-based model, that is tachytron 2 baseline architecture. If we look at the results of these different ablation of these different architectures, we will see that our candidate system seems to outperform the baseline for all different data amounts. So that is the baseline based on our previous work on attention-based technology, as well as it seems to outperform a full data baseline. So that is the baseline trained on a single speaker, on a single target speaker for about 10 hours, which is a significant result. And we can see that our candidate system is even better than a full data system trained on, sorry about that. We can see that our candidate system is better than even a full data system with the same architecture when we have 1 or more hours of data for our target speaker. And the one limitation that we've noticed is that the conditional GAN fine tuning seems to only bring an improvement when we have more than 3 hours of target speaker data available. One note about the results presented in this table is that we conducted this experiment on 4 different data amounts independently, and the listeners for each test is in each data amount are independent. So the results are not transferable. The numbers are not comparable across the columns, but we can see that with as little as 30 minutes or more data, our candidate system seems to outperform baselines with both the same architecture as well as with additional 7.5 hours of data. So this takes us to conclusions and future work. And what do we conclude? We have a system that we can produce robust, high quality natural speech with as little as 15 minutes of recordings, and for even the most challenging expressive voices. And we have outperformed the state of the art in both naturalness and similarity by closing the gap to recordings by 23% and 16% respectively. So we both address the limitations of the current state of the art in the axis of expressivity, as well as we push the performance of the current state of the art in low resource text to speech. Where do we see to take this technology into the future? Well, on the data side, we are looking to apply this technology to other more challenging voices, such as expressive voices in multiple languages. We saw some interesting discussion about multi-speaker text-to-speech across multilingual corpora in yesterday's presentations. We could also look at more challenging voices than human voices, such as character voices, which have an even higher amount of expressivity. On the architecture side, we are looking to investigate further this architectural change of external duration modeling by looking into the differences between joint and external training of this duration model, and to see what effects it has to our techniques, in particular to stuff like fine tuning. And lastly, to get even closer prosody, we are looking to investigate improving our baseline architecture with more fine-grained prosody modeling, such as hierarchical and phoneme level autoencoders. So that takes me to the end of this presentation. Welcome any questions that you guys have. Thank you.
Thank you very much for the presentation. I can see that now we have a couple of questions in the chat. First, in the beginning of the presentations, Simon King wrote that without sample, it's really difficult to know what you mean by highly expressive. I had the same question is in mind, that is there like a definition for highly expressive here?
Yes. So the way we measured highly expressive here, unfortunately, it is a shame that we can't share samples. If you could listen to these samples, it would be clear to intuition that these voices are more expressive than neutrally recorded voices. What we do mean, and we analyzed objectively as highly expressive, is in terms of variation in energy, fundamental frequency, and phoneme durations. So we analyzed the mean and variance of these three features across within the utterances for a speaker, as well as their derivatives. So the changes in these features in frequency, energy, and duration within an utterance for a speaker. And we form a heuristic of expressivity that is based on the combination of these. Voices that are outlying from the mean of a large speech corpus were deemed to be highly expressive outliers, and the degree of their deviation from the mean of a standard neutral corpus is what determines them to be highly expressive. So that's how we measured this objectively. And conversational voices were voices, I can see your further question. Conversational voices were voices that were slightly outlying from the mean, so within a standard deviation from the mean of a neutral data set. And highly expressive voices were those that were more than one standard deviation outside. And I think this was the most challenging voice that we had evaluated in these objective criteria, as well as in terms of subjective listening, also clearly the most expressive voices.
We have a couple of more questions in the chat if you go up. So after Simon's question, we had one from Raahil. What is the differences between your no attention architecture and other like fast speech tool?
Yeah, so before I get to that question, I'll just address a couple, the follow-up from Simon King. Can we play some non-confidential samples? Unfortunately, because the voice is that of a celebrity voice, our contract doesn't allow us to publish those samples publicly because of the contract with the celebrity. So that is a real shame. Back to the question by Javier. What is the difference between a no attention architecture and other architectures like fast speech 2? So one of them is because we are looking to tackle expressive voices. We think that prosody is something that is important to model on its own. So we have left room for prosody modeling with a variational autoencoder right now at the global utterance level. But we seek to improve on that by looking at word and phoneme level prosody models explicitly. That is a difference with fast speech 2, doesn't employ autoencoders. And fast speech 2 also explicitly models pitch and frequency, which we don't have in our current architecture, but this is an architecture we are currently exploring. So as we see it, this architecture is somewhat of a hybrid between current non-autoregressive techniques, such as fast speech 2, parallel tachytron, and non-attentive tachytron that have been published out there. Yeah, so looking at the next question in the chat, do you sample from all points in the VAE latent space at inference to produce different variations of expressivity? So because we are trying to synthesize only for the target speaker, we have very little data for our target speaker that is present. So about 15 minutes is a few hundred utterances. What we do is a technique my colleague would have mentioned yesterday is take a centroid of these utterances. So we take an average of the latent space projection of these utterances that we have. Selecting a better prosodic latent at inference time is something that we can look into, but hasn't provided as much of an improvement as we can, as has with the other parts of the techniques that we have introduced. So I think something like duration modeling significantly improved the degree of expressivity that we could produce. But yes, interpolating within the latent space is something that we will continually look into. We do use this technique for something like questions, where there is a known different intonation and prosody expected with questions, to take, say, a different average of latent utterances for questions rather than for statements. But the results presented in this paper use a centroid computed on all of the limited samples of our target speaker. Let me move on to some of the other questions. So yes, the definition of conversational and expressive, I think I've covered, and I will provide some public links about the samples we can share. In the current work, the encoder is shared between the acoustic and duration model, or are they separate? Is this what you mean by joint training? Exactly. So that is exactly what we mean by joint training. In the current work for our candidate architecture, the acoustic model and the duration model are trained separately. So that is the phonetic encoder that is based on the Tachytron 2 architecture. There is a separate one for the acoustic model, and the duration model is a separate model that is trained separately for a different amount of steps. The architecture that Simon is presenting, which is the joint training architecture, is something that we briefly looked into. For the current use case, it was performing worse than the separate training architecture, which is why we went with that for the results that we have here. And that's what we will look into in our future work, is to understand how to bridge that gap, because we see joint training as a more scalable architecture in the future, where we share the phonetic encoder between the duration and the acoustic model. And the phonetic encoder then also learns from signals that the duration model is learning from. So yes, that is something we'll look into, but our current work uses a separate training or disjoint training of duration and acoustic models.
And we have a couple more questions at the end from Bastian Schnell. Can you please answer them quickly? Because we should go to the next presentation, and I suggest that there is a lot of interaction. You can continue it later in the spatial chat, for example, in the coffee break. Yes. So I'll go through Bastian's question. Your results were an expressive celebrity voice. Did your improvement fix the 3 problematic voices? How are the other 7 voices affected? So although not published in this paper, we have used this technique onto the other voices that we are presented, that we discussed. I believe it does improve the 3 problematic voices that we presented earlier, bring them above the 80% Mashra requirement that we presented in our previous work. And we've also been experimenting with this technique on multilingual voices that are both conversational and expressive. So more on that will be presented in future work, I hope. And did you evaluate more on cropping 64 frames for the discriminator? Yes. So why we think this is beneficial? We think that it is easier for the discriminator to discriminate on cropped mel spectrogram frames, as well as for the phoneme conditioning information to provide use with smaller segments of the mel spectrogram. We did try with training the GAN to discriminate on the entire mel spectrogram sequence, and we found this technique to be better. And we hypothesized it is because of a more weighted signal for the phonetic information, which we see is useful from our ablation study. And lastly, we did not use a speaker-dependent neural vocoder. This was using a speaker-independent universal vocoder for all of our evaluations. Yeah. Thank you very much. I will take further questions in the chat or otherwise.
Yes, hello. I'm curious, so you compute duration for each phoneme. What about pauses? How you compute pauses and how you assign pause duration and how you ensure that the pause duration is compatible with pre-pausal lengthening. Do you hear me, or just is there anybody at the end of the line? He disconnected. No more question. Yeah.
So we were. Can you please come here?
Come here.
Otherwise, they will not hear you.
So we simply did forced alignment, and that provided us with both the duration of phonemes and pauses. And forced aligner was able to insert the pauses on each word boundary.
So how? It's not clear for me. So pause, no pause. Where is that decided?
Where this is decided. This is decided by forced aligner, right?
But at the synthesis time.
At synthesis time, so it depends like how you set it up. In the vanilla setup, it just every punctuation mark means pause, because this is intuitive for the user, because they want to insert the pause, they just put a comma, for example. But if you synthesize something longer, it makes sense to introduce the phrasing model, which would either remove the phrase breaks on the commas and insert them when there is no punctuation.
Okay, thank you again for this presentation. And the next talk, it will be by Paul Konstantin Krug from the TU Dresden, Germany. And the topic is Intelligibility and Naturalness of Articulatory Synthesis with Vocal Tract Lab compared to established speech synthesis technologies. So please start your presentation.
Yeah. So thank you for the introduction. Let's talk about articulatory synthesis. I'd like to start with a very brief recap of the history of speech synthesis that actually started over 200 years ago, where people started to build mechanical speaking machines and talking heads. And what's interesting is that from yesterday, from one of yesterday's talks, we know that talking heads are now still a thing 200 years later, which is amazing. But anyway, things progressed in when electrical circuits were invented, and formant synthesis came up. You could see the formants on spectrograms, and then people discovered that you could synthesize them, and then later also concatenative synthesis came up, where you would concat pre-recorded speech units such as phones and diphones, and then later this turned into unit selection, which would form powerful hybrid models when combined with the HMM model-based synthesis. And that would be the state of the art until very recently, when neural networks were basically rediscovered and well, took the world by storm, and now everybody uses them because they perform really well. However, the interesting thing is that articulatory synthesis, which is the simulation of the vocal tract, was always part of the research domain. However, it never really had commercial success. There were really very few commercial applications of articulatory synthesis, and it's compared to the other models, it's rather unknown, and that's even despite the fact that it has certain advantages over recent models. That is, if you want to, because of the high flexibility of the vocal tract simulation, you can easily turn neutral speech, for example, into emotional speech, or you can change the speed or the pitch of your synthesized speech easily compared to model-based approaches. So what is the problem with articulatory synthesis is that it requires a very deep, a very precise knowledge about the how speech is produced inside of the human vocal tract. You need a lot of phonetic knowledge, and for a long time there was just no complete aerodynamic simulation and no complete models of, because there are many steps involved, yeah, so it's another reason that's problematic. And then finally there were always better sounding methods available, which were easier to use in the sense that they don't require that huge amount of explicit knowledge about speech production, and therefore you could also build TTS systems easier with those systems, because articulatory synthesizers usually require a lot of manual tuning that can only be performed by experts. However, recently the articulatory synthesizer vocal tract lab was released in a new version, which includes a phoneme to speech functionality, and you can actually turn this into a text to speech system. So I want to present this system here, and then the goal of this study is to give a fair comparison of vocal tract lab, which is basically the state of the art when it comes to articulatory synthesis, with 8 other text-to-speech systems, which are either state of the art now, so neural synthesis, or represented the state of the art of speech synthesis once. So, for example, HMM-based methods or a unit selection synthesis. And we evaluate these systems in terms of speech intelligibility and speech naturalness, and we include natural recordings as a reference in our experiments. Before I continue to describe the study, I want to give a brief overview or brief introduction into the vocal tract lab. Vocal tract lab is an open source articulatory synthesizer that is provides a one-dimensional aeroacoustic simulation within a vocal tract model, which is based on MRI scans of the human vocal tract. On the right, you can see a 3-dimensional rendering of the vocal tract model that is used for the simulations. And during speech simulation, these vocal tract would move dynamically, and it's would produce speech. So we can listen to this.
Chabos wissen, wer der Babo ist.
So the vocal tract lab gives us full control over all the articulators and the glottis model. It's not limited to German, so you can in principle produce any kind of sentences or utterances. However, the phoneme to speech functionality that the software currently offers is limited to German at the moment, because it involves some preset shapes of the vocal tract, and these preset shapes currently only exist for German. The software offers a graphical user interface where you could define a sequence of phonemes on a timeline. So you could define these little segments which represent phone durations, and they include, so you can enter a phoneme in the Zampa representation and then build longer utterances with this. So this would be the sentence, aber sehen will sie ihn doch, which in English means, but she wants to see him. And you could then basically press a button and turn this into a so-called gestural score. I know that this looks scary, but it's just several different tires which represent time functions which describe the vocal tract dynamics during the simulation. And the nice thing is that you could tune all these time functions any way you like, so you have full control. Or you just go with the pre-calculated values here, and then you could synthesize your speech. And if you want to do an articulatory resynthesis, you could do it by loading a natural sample into Vocal Track Lab, and then you could copy the phone durations from the natural utterance, and you can also copy the pitch, and then you will end up with a sample that sounds quite like the natural recording. Of course, the voice is different, but the pitch and the phone durations, so it will sound kind of similar. So how can we extend this into a text-to-speech system? Well, you need to turn the text into the phonemes. So you need the G2P conversion. You have to predict the intonation, and you also have to predict the phone durations. And currently, this pipeline was developed in cooperation with a German company called Articulation. So they provided us a web service that basically gives us the G2P conversion and the syllabification, as well as some linguistic features such as part of speech tagging and stress marker insertion. And these features are important for the prediction of the intonation, which is done by a simple neural feed-forward neural network, which predicts 3 parameters per syllable, which describe the pitch contour in this syllable. And the phone durations are actually taken by predetermined values from a study from Bernd Möbius and Jan van Santen from the 90s, actually. So this pipeline, of course, has room for improvement, but so far it already works as a text-to-speech pipeline. So in our study, we synthesized 15 German sentences using several different systems. We used two commercial systems with 4 different voices. So we used 2 neural voices from Google and Microsoft, as well as their standard voices provided by their web services. And we can listen to these.
Aber sehen will sie ihn doch.
So that's the neural voice. Then here we have the standard voice.
Aber sehen will sie ihn doch.
Then we have the Azure one.
Aber sehen will sie ihn doch.
Aber sehen will sie ihn doch.
So we can hear that the neural voices, of course, sound very good. Then we have the Vocal Track Lab text-to-speech system, and we also use the resynthesis because the resynthesis can give us an idea of the upper limit that we can reach with a text-to-speech system if the pitch prediction and the phone prediction were really good. So we can listen to these as well.
Aber sehen will sie ihn doch. Aber sehen will sie ihn doch.
You can already hear that the TTS system sounds a bit more boring because the pitch contour is more flat, and the phone durations are a bit longer. And then we use for other voices that were developed at universities. That's the unit selection voice developed by the DFKI, which is a German Research Institute for Artificial Intelligence. They made a unit selection voice and HMM voice for the synthesizer Merritt TTS. You can listen to those.
Aber sehen will sie ihn doch. Aber sehen will sie ihn doch.
And we also used a diphone-based resynthesis because we could directly compare that with the Vocal Track Lab resynthesis. And then we have a diphone TTS system which is dress, which is already quite old.
Aber sehen wir sie ihn doch.
Aber sehen will sie ihn doch.
Yeah, and you can hear it has some artifacts, but then ultimately we also used, we recorded natural speech as references.
Aber sehen will sie ihn doch.
And all these synthesis systems were used with the male voice and a neutral speaking style and a neutral tempo. So how do we measure the ASR? Well, the intelligibility, sorry. We use ASR to do this because if we would present the samples to human listeners, you would have to do it in a way that they only hear a single technology, because otherwise the better sounding samples would bias the results, because you could, if you can understand the better sounding samples, then you would probably also understand the worse sounding samples. So then you would need a lot of listeners, and yeah, it was just easier for us to use state-of-the-art ASR systems instead, and therefore we used 4 different web APIs from Google, from Microsoft Azure. Then we used a service called WitAI, which is owned by Facebook, and then we have the IBM speech-to-text service. And on the right, you can see a plot. So we send it all these samples that we created. So we have 11 systems and times 15 sentences, so 165 samples to these services. And from the returned strings, we would calculate the word error rate. And this is what you can see here. So the median word error rate is 0 for all the distributions. So that means that most of the times the samples would be recognized correctly. However, there's still a significant difference between, for example, Google and WitAI and IBM. But there is no significant difference between the Google and Azure systems, and between Azure, Wit, and IBM, there's also no significant difference. So in order to reduce possible biases, we went with the answers from all those systems. And if we look at the different systems, we can then see that the commercial systems are basically as intelligible as natural speech already. And there's a gap between the commercial and academic systems, which are less intelligible. However, we don't find a significant difference among these academic systems. However, we can clearly see that for most of them, the medians of these distributions differ from 0, which is not the case for the natural systems and the commercial systems.
Paul, sorry to disturb you.
Yeah.
I would like to ask you to speed up a little bit with your presentation,
yes,
because we are already 50 minutes, so please focus on the results. Thank you.
I will do. So we also did a liquor test to test the naturalness in a listening experiment with humans, where we had 50 participants, and we also used a kind of automatic speech quality assessment. There we used a pre-trained CNN LSTM based model, which is called NISCA TTS from last year, I think. And from the listening experiment, we see that natural speech is of course considered the most natural. And then we have the neural synthesis, then the commercial standard synthesis, which are a mixed base of unit selection at HMM synthesis. And then we basically see a plateau where we have the HMM-based academic synthesis and the vocal tract lab resynthesis and the Embrola resynthesis, which are not significantly different from each other in this with regard to the score. However, all other combinations would be significantly different here. And the NISCA results. So basically, the idea was to test this system because it has never seen articulatory data, for example, in the training samples. So, however, we saw that the vocal tract lab synthesis are really overestimated in performance, and the neural synthesis in natural speech would be underestimated. And overall, the correlation between the predicted MOS scores and the measured MOS scores are not very high, unfortunately. Because it would be very easy to use such systems as a replacement for sophisticated listening tests. Okay, so to summarize, we found that no text-to-speech system is as intelligible and natural as human speech yet. So even for the neutral speaking style, speech synthesis is still not done yet, which is good because that means we all still have jobs for a few years. But anyway, commercial systems significantly outperformed the academic systems, but we also saw that the vocal tract lab resynthesis was very competitive within the subgroup of academic systems here. And we could also see that the vocal tract lab text-to-speech pipeline has room for improvement, because in terms of naturalness, it was worse than the resynthesis. So of course, it can be improved with better pitch and phone duration modeling. And last but not least, we also have, so in order to improve the intelligibility of the vocal tract lab, we have to improve the simulation itself. And starting points for this are, for example, the noise sources that are active during the simulation, because the noises are very important for the intelligibility of consonants and consonant clusters, for example. Yeah, and if there are still questions, I will be happy to answer them now.
Thank you very much for the presentation. We can have questions both from the chat and also from the local audience.
Who is ready for a question?
Please, Gerard.
So it's perhaps a question for Peter Beckholz, but I'm questioning the overall philosophy of your work, of your system. F0 is an acoustic parameter. Okay, normally it's produced by articulation, by the laryngeal muscles, and so on. So I'm questioning about the interplay between acoustics, which is the target. You want to produce a sound, and the articulation. For example, when you do copy synthesis, it's very unclear, you adjust by hand and so on. So do you have an inversion system which tries, in fact, to infer articulatory parameters which best generate an acoustic waveform? So what is the general philosophy in terms of control?
So we are also working on inversion systems, which try to predict the articulatory movements from the acoustic domain, for example, but it can also be used, the vocal tract lab can also be used as an interface for, so you can in principle put in articulatory data that you measured in order to control the synthesizer. So it can also be used as the forward model in a silent speech interface, for example. Yeah, so it has different applications.
Natively, you don't have any acoustic score, in fact, computed. Because if you want to reach a quality which is comparable to end-to-end synthesis, somehow you need to have some hints about what are the key points, the acoustic key points, so that to guarantee that you have a successful, for example, phasing relation between articulatory movements and so on. So for me, it's very unclear how you will move forward in order to get a proper coordination that guarantees that you have the good phonetic features at the end. So the controller of your system, for me, is very unclear in which direction you are going. Perhaps it's not clear in your mind also. So.
Yeah. So controlling the synthesizer is difficult, and evaluating it, you cannot directly compare it to the voice that was the base to model the synthesizer, because that's just not available. But you have to establish either establish the acoustic to articulatory inversion mapping, and then evaluate this in listening tests, or you just by manually fine-tuning things, and by making rules, basically a rule-based approach, you can try to get the speech as natural as possible, but it's difficult. Yeah.
Thanks. Thank you.
Also, we have a question in the chat from Mohammed Al-Arathi, that you mentioned in the beginning that 70 linguistic and phonetic features are mapped to 3 parametric features.
Yeah. So the 3 features that you predict, these are basically that's basically a linear function. So the vocal tract lab is the time function that I showed. They are based on the target approximation model, and what this model is doing, it describes each syllable as a linear function, and then the time function will be the response of a low pass filter to this underlying linear target. And so 2 of these parameters are the offset and the slope of the linear function, and the 3rd parameter is a time constant that describes how fast the filter is acting, basically.
Thank you. And the question from Alex is, what is the tool behind the presenter?
Yeah, it's you can turn on off the current things.
Thank you very much again for the presentation and for answering your question. And our next speaker will be Ambika Kirkland from the KTH Sweden, and the topic is perception of smiling voice in spontaneous speech synthesis.
All right, let me just get the presentation started and share my screen. Second. There we go. All right. All right, so I'll be talking about the perception of smiling voice in synthesized spontaneous speech. So just to kind of give a brief background on the function of smiling in interpersonal communication. So smiling influences how cooperative, how trustworthy or extroverted someone seems, how sympathetic or kind. It serves a lot of different functions in communication. And this is not just a solely visual phenomenon, but smiling actually creates perceptible changes in speech. So you know, when you smile, you spread your lips, and this particularly affects certain vowels that like rounded vowels, where you normally have your lips sort of rounded, and when you smile, your face spreads out, and that changes the quality of your speech. So what this means is that this smiling voice can convey the social functions of smiling in the absence of any kind of visual cues. And so what is this? What are the features of this smiling voice and naturally produced speech? Well, smiling voice tends to be characterized by greater pitch, height, and range, and by higher formant frequencies for some vowels, particularly rounded vowels. So I guess I won't spend a huge amount of time on this, but there's been some previous work on synthesizing this smiling voice or smiled speech or whatever you want to call it. There was an approach, for example, that used articulatory synthesis, and they just synthesized some German vowels. So this is sort of not really kind of like a general synthesis of someone, you know, speaking with an amused speaking style or something like that. It's basically just making vowels sound the way that they would sound if someone produced them while smiling. But that's also interesting because they show that even, you know, people can even hear the difference in simply isolated vowels, which is kind of neat. Approaches using hidden Markov model synthesis trained their models on red speech. So they had a voice actor who would read some passages in a neutral speaking voice, and then they had a voice actor read the same passages in while smiling. And so in this case, they elicited the smiling in the training data. They asked the voice actor, okay, smile, sound amused, don't laugh, but smile. And then they interpolated between these different models to create a model where you could control the degree of smiling. And that worked pretty well. However, the speech that sounded more as if the speaker was smiling also sounded less natural. And I guess I should also mention previous work that looked at tried to synthesize laughter as well. Typically, these have kind of been treated as two different independent components that were sort of synthesized independently and then combined together. So some of the questions we had in goals for this paper were, so can we synthesize smiling voice just using spontaneous speech data, where smiling and laughter are not things that you're explicitly eliciting. Of course, they have to be present in the training data, right? But you're not asking the voice actor, okay, sit there the entire time and talk with a smile on your face and sound amused. It would also be kind of interesting if we had a setup that would let us synthesize both smiling voice and laughter, which, I mean, smiling and laughter tend to co-occur. So it would be interesting if we could produce both of these sort of at the same time. And it would also be good if we could synthesize smiling speech without making that smiling speech sound unnatural, less natural than the non-smiling speech. So the database that we used was a spontaneous speech corpus. It was audio recordings from the Trinity speech gesture data set. So this consisted of 25 impromptu monologues in Irish English. So it was basically this guy who was sitting there and just sort of recounting amusing anecdotes and just sort of talking off the cuff on average for about 10.6 minutes. And there was a good bit of laughter and smiling present in this data. It was sort of recounting amusing things. This data was transcribed with automated speech recognition, and then it was manually corrected. This automatically transcribed speech was then enhanced with manually annotated aspects. So filled pauses like and laughter, style breaks, silent pauses, which were indicated with a comma. And these were all transcribed using ARPANET phones. So we didn't come up with there weren't any sort of new characters that were used to indicate laughter or anything like that. And I guess I won't go into excruciating detail about this, but the speech was segmented into these breath group bigrams where you have these sort of utterances composed of speech that sort of overlaps. So you have here utterance 1 and utterance 2, and this is the last part of utterance 1 is sort of the first part of utterance 2. And this setup gave us sort of longer utterances, but and also allowed us to for learning contextual information during training beyond respiratory cycles. Right. Just a sec. Okay. Sorry. Okay. So in terms of synthesis, we had two systems that use the sequence-to-sequence neural TTS engine Tachytron 2. The first system we referred to as an unconstrained system that just uses a standard Tachytron 2 architecture. System 2 we're referring to as the constrained system, and this uses like a utterance level prosody control. So the speech rate in terms of syllables per second and mean F0 are normalized to the utterance level based on the median values in the corpus. The smiling voice, so the way that was synthesized was basically we had laughter that was annotated in the training data, as I've mentioned. And so we would expect that speech directly after laughter would involve smiling, unless you're a supervillain and you're like, and this should in turn result in some acoustic differences in the speech following laughter. So accurately reproducing these differences in the synthesized speech should reduce the loss function during training. And in our synthesized speech, we should find that the speech following laughter has similar characteristics to the speech that would follow laughter in the training data. So we included this laughter in the text to be synthesized. We basically wrote before the utterance that we were synthesizing. Just a sec. All right. So in total, we had 36 utterances, and these utterances would express a positive, a negative, or a neutral opinion. We removed the laughter and the inhalation breaths from the beginning of the utterances because otherwise the participants listening to these stimuli would have just could have just based their decisions on hearing the laughter beforehand or hearing the inhalations, which we notice a difference in the inhalations preceding the inhalations following laughter. So we remove those from the utterances, and I have some samples here. So I'll point out some of these stimuli, I think at least that you can hear the difference more clearly than others. And I tried to pick some where I feel like the difference is relatively clear, but there's a few of them where I'm not sure that I could hear it either. But whatever the case, right, I'll go ahead and play some of these samples. So this is
That's true.
This is non-smiling.
That's true. That isn't necessarily true. That isn't necessarily true. I'm good with both options. I'm good with both options. That's true. That's true. That isn't necessarily true. That isn't necessarily true. I'm good with both options. I'm good with both options.
Right, and all of these stimuli can be seen at this link that I've included here, which is also in the paper. So you can listen to all of the stimuli if you want. Like I said, some of them, I feel like there's a much clearer difference, whereas others are a bit harder to tell the difference between them. Oh, sorry, what's going on here? Ah, why isn't it going to the next slide? Jesus. Just a sec, I'm just gonna. So, all right. So the first thing we did was we looked at the acoustic and prosodic characteristics of the synthesized speech. So we wanted to know whether they varied based on whether we used the constrained or unconstrained model, whether they were following laughter or not following laughter, and based on whether the opinion expressed was positive, negative, or neutral. So first of all, we didn't find any differences in mean F0. However, we did find that for speech following laughter, there was greater variation in F0. The unconstrained model had a higher speech rate, which I guess would make sense because with the constrained model, we normalized the speech rate to the median values of the corpus. We also found that the constrained model was higher in a measure of breathiness, or well, lower, but sorry, lower in a measure, higher in the measure of breathiness, but that indicates more breathiness. Sorry, that's a bit confusing. What we probably should have done and would do in the future is to look at the actual acoustic and prosodic features of the post-laughter speech in our training data. So we should have and would in the future look at what this actually sounds like in our corpus, what the features of that post-laughter speech are in our corpus. Right. So we used a Mushra-like naturalness test, and we had 21 native speakers of English that we recruited on Prolific, listen to these speech samples and rate how natural they sounded. There wasn't really much of an effect of anything here. The only thing we really found was an interaction between the model, so constrained and unconstrained, and the content, so positive, negative, and neutral. But none of the simple main effects were significant. It's not really easy to interpret what this means. But importantly, though, we didn't find that the post-laughter speech sounded less natural. We also wanted to know whether the participants could tell the difference between these the post-laughter speech and the other speech, the smiling and non-smiling speech, and whether one of them sounded more like smiling than the other to them. So we recruited 60 native speakers of English, again on Prolific. Half of them listened to stimuli from the constrained system and the other half from the unconstrained system. So that was a situation where we divided the participants into two different groups, but all the participants listened to all three types of content and context. All right. So what did we find? Well, first of all, the post-laughter speech was identified as sounding more like smiling at a rate that was significantly higher than chance. It's around 62%, I think. Higher for the higher for the unconstrained model and lower for the constrained model. Discriminating between the smiling and the non-smiling speech seemed to be easier when the content of the utterance was positive. However, because of this sort of forced choice setup that we had, this doesn't really let us conclude that the positive content increased the likelihood of perceived smiling. Basically just meant that the participants could more easily distinguish between the smiling and non-smiling speech. So maybe the system was better at generating utterances that sounded like smiling when the content was positive. And it was harder to discriminate between the two samples when the speech was synthesized with the constrained model, but it was still better than chance. All right. So yes, it does seem that we were able to synthesize smiling voice with spontaneous speech data. Although kind of a drawback here is that, you know, this forced choice setup for the perceptual experiment means that we're not really 100% sure that the participants really differentiated between them on the basis of how much they sounded like smiling, because we asked them to differentiate between them on that basis. But it may well be that there was some other perceptually salient difference that doesn't really have anything to do with whether they sounded like smiling or not, and the participants kind of forced to make a choice, discriminated them between them on the basis of that. So that's entirely possible. In the future, we might want to have a more sensitive means of measuring how amused sounding our synthesized smiling voices in the future. This approach could allow us to both create a smiling voice that emerges in the context of laughter and have the laughter and the smiling voice together in the synthesized speech, or just sort of standalone amused speech where we mask the synthesized laughter in the output. And finally, it seemed that the speech following laughter was not perceived as less natural than the non-smiling speech. Okay, that's it for me, I think. Any questions?
Thank you very much for your presentation. We have a couple of comments in the chat. There was a comment by Simon during the presentation that you are not sharing the audio. I think you were sharing the audio. It was just very soft compared to your microphone signal.
Okay.
So I don't know if you can add some more volume. Could you please?
Yes, I can try that. Just a sec. I'm not entirely sure how to adjust the volume on PowerPoint. That's, oh goodness. Just a sec. I'll adjust the volume on Zoom. That should help. Maybe it'll make me really, really loud, but input level is on maximum, so I don't really know. Oh, sorry.
Much about that, but we also have a question from Ayush Pandey. Yes.
Thank you. Yeah. You can listen to them there. Yeah.
Okay, great.
I'm sorry about that.
No problem. Can you see the question in the chat?
Yes. So just a sec. Question about acoustic prosodic analysis. Would it help to separate acoustic features by category? Do you expect phonetic segments that involve bilabial involvement should be affected, more affected than those produced dorsally? Yeah, absolutely. So I mean, look, people that have looked at smiling voice in naturally produced speech did find that this to be the case. So I expect that if we had done sort of a more detailed analysis, we would have probably found something like that as well. Yeah.
Also, I have a question that with the way of this post-Lauter synthesized speech, that so there were in the stimuli there were shorter and longer sentences, and even during the longer sentences, is the full sentence smiling or just the beginning, or how are these samples? Yeah, so I mean, we didn't really specify that the participants should focus on a particular part of the sentence, and it's true that they varied in length. So it's also, you know, possible that for the longer sentences or something like that, then the effect might have gotten diluted a bit. You know, I'm not entirely sure. But I would imagine that probably the segment of the speech that was closest to the laughter might be more colored by it than in the longer utterances. Yeah. Thank you. And I have a last question that, okay, so the smiling synthesis works for short sentences, and how to integrate this to conversational AI? So I don't know, which sentences should be smiling? Yeah, no, I mean, it's a good question, I guess. Because I mean, I assume you don't want to have some conversational AI that's just sitting there with this massive grin the entire time, right? So I mean, one possibility could be if you had some sort of conversational AI that's also taking some input from the person that's talking to them. It's, you know, generally a good idea to mirror the other person's behavior. So if the other person were laughing and smiling, then that might be the appropriate time to insert some laughter. And if you're using a setup like this, where the smiling is kind of directly connected to the presence of laughter, then that you know, helps out to an extent, because then you have this, you know, you synthesize the laughter, and then a certain amount of the speech afterward is colored by the laughter and sounds like smiling, so that you don't, you know, have an issue with just, you know, all of the speech just sounding as if the person has a gigantic grin on their face. So. Yes. Okay, thank you very much again for the presentation and the answers. Thank you. And the last presentation in this session, it will be given by Thomas Drugman from Amazon. And the title is Voicey, Zero-Shot Non-Parallel Voice Conversion in Noisy Reverberant Environments.
All right, thanks a lot. Thanks a lot, Tamás. I'll try to keep the smile as well. Can you see the screen? Yes. Right. Okay, cool. Thanks a lot. So yes, thanks for that. Thanks. So indeed, I'm going to present Voicey, which is a technique for zero-shot non-parallel voice conversion, specifically targeted for noisy and reverberant conditions. The main contributors are Alejandro Muttini and Jaime Lorenzo Trueba, and I myself, I'm Thomas, and we come from Amazon. All right, so some background. The task here is voice conversion, which I guess you know is the task of modifying the speaker identity from a source speaker to a target speaker while keeping the linguistic content unchanged. If you look at the literature for voice conversion, majority of the techniques suffer from some limitations, such as they are trained and evaluated only on clean speech, or they cannot perform what we call non-parallel zero-shot conversion. So non-parallel means that during training, there is no paired aligned data between the source and target speaker. And zero-shot even means that during training, the source speakers are unseen. So it's pretty challenging. And Voicey targets to offer the following benefits. First of all, it's tailored for noisy and reverberant scenarios. It it targets non-parallel zero-shot voice conversion. It is based on denoising autoencoders and builds upon AutoVC, which is this paper from Cohen et al. From ICML 2019, I think now pretty standard in voice conversion. And the technique is meant to be robust and easier to train compared to conventional techniques like GAN or flows. So the system itself consists of 5 modules. We have 4 types of encoder. We have a speaker encoder, there is a content encoder, a phonetic encoder, and a acoustic ASR, so automatic speech recognition encoder. 4 encoders, which are then fed into one single decoder. We use 2 types of representation of a given utterance, the MEL spectrograms extracted from the audio, and during training, we also use the phonetic transcription of the utterance. So as I said, there are 4 encoders and they are meant to capture different dimensions of speech. ES is the speaker encoder, which is here to capture the who, so what is the speaker identity. EC is the content encoder, here to model the how, so what is the prosodic information in the utterance. And finally, you have the phonetic and SR encoders, which are here to capture the what, so what is the linguistic information. This is the architecture of the system during training and inference times. Don't worry, I know it looks pretty complex. I'm going to dive deeper into that. But just as you can see here, we have ES, the speaker encoder, the content encoder is here, the SR encoder, and the phonetic encoder. So those are the 4 encoders, and we have one single decoder here consuming the embedding from those encoders. So let's dive deeper, as I said, and I'm going to focus on this slide on this red rectangle where we do have the speaker encoder and the content encoder. The speaker encoder follows the architecture from this paper from One et al. So it's a speaker verification speaker verification system. It's a paper from ICASP 2018. And the speaker verification is pre-trained on the VCTK database and it's frozen during training. The content encoder is here and it's largely inspired by AutoVC with only modification to the hyperparameters. So this part here actually is, I would say, very standard and builds upon AutoVC. The main novelty is this red rectangle here in the bottom, where we have the phonetic encoder and the SR encoder. So the phonetic encoder takes as input the phonetic transcription and encodes the sequence of phoneme into a sentence level representation. And its goal is to maintain a high intelligibility. The ASR encoder, which is here, its goal is to produce embeddings which are as close as possible to the phonetic embedding. And actually during inference, because we don't have any phonetic transcription of the utterance, so this phonetic encoder here during inference will be removed. And the goal of the SR encoder is to substitute it. So we want to produce embeddings which are as close as possible to the phonetic embedding. So therefore, ASR takes as input only spectrograms, only the audio, and doesn't use any phonetic transcription. On the top right here, rectangle, we do have the decoder, which takes as input the embedding from the speaker encoder, the content encoder, and during training, the phonetic encoder. It's based, again, very standard, it's based on AutoVC, and as output, it provides the converted spectrogram, which itself, it's fed into the nerve encoder. And for that, we use our robust, our universal wave RNN vocoder. So what else can we learn from this architecture here? So this notation here, A means this is the audio, so the spectrogram, it's speaker 1. So we convert speaker 1 to 1. So which means that during training, the target speaker and the source speakers are the same, right? And I here means the utterance. As input, as you can see, we use the same speaker 1, but we can use different utterances in the speaker encoder or in the rest of the network. And finally, This is a target that we want to reconstruct. We use a tilde here to indicate that it's a clean version. So basically during training, we are going to use clean recording, but also data which is artificially corrupted from those clean recordings. So we add reverberation or we add noise, right? And the goal during training is always to reconstruct the clean version of the spectrogram. So that's what we call the denoising autoencoder paradigm. The total loss consists of 3 losses. We do have a reconstruction loss here, which is L2 norm between the target spectrogram and the converted spectrogram. There is a phonetic loss over here, which is L1 norm between the phonetic embedding and DSR embedding, because again, we want DSR embedding to be as close as possible to the phonetic ones. And finally, the content loss here, which is the same as used in AutoVC. During the inference, first of all, as you can see, the phonetic encoder has been removed. Indeed, we do not have any phonetic transcription during inference. So we just use instead DSR encoder over here. We have 2 speakers, speaker 1 and speaker 2. Speaker 1 is a source speaker, and the utterance is fed into the content and DSR encoder. And speaker 2 is a target speaker, which is fed into the speaker encoder. So that means that the decoder here is going to reconstruct the spectrogram as if it was uttered by speaker 2 by the target speaker. The experimental protocol, so we use 3 data sets. As clean recordings, we use the normal Libre speech data set, where we have about 1.2K, in total 1.2K speakers and 460 hours. And then we have 2 versions which are artificially corrupted. We have a scenario where we have only reverberation, and then we have additive noise plus reverberation. So how we create the reverberant data set, we use the Aachen impulse response database with a wide range of settings for the impulse responses. Noise plus reverberant scenario, the 3rd version of the data set, if you wish. We use a pyroom acoustic simulation package. We create rooms with different sizes, and we can place the source of noise in different locations. The noise itself can be white noise, or we can use external noises from the demand data set. And the SNR varies between -2 to +35 dB. I'm going to play some samples. Please shout out if you can't hear. But just samples of those data sets in clean, reverberation, and noisy plus reverberation.
Over the fireplace, there was a large, old-fashioned gilt mirror.
His instant of panic was followed by a small, sharp blow high on his chest. It is obviously unnecessary for us to point out how luminous these criticisms are, how delicate in expression.
Okay, I hope you could hear that properly, and also that you can appreciate the fact that they are pretty adverse conditions. The conversion, so we use 2 target speakers randomly selected, 1 male, 1 female, and we transform fraudulent utterances from the test set. The techniques that we compare are voicey, which is a proposed technique here, which I just described. As baseline, we use AutoVC, so that paper from ICML 2019. AutoVC with some pre-processing. So before the audio to be fed to AutoVC, we use techniques for denoising and de-reverberation. Stargan VC, so I think relatively standard for voice conversion, a paper from Hameoka at SLT 2018. And a last system that we called phonetic, which is basically voicey, right? But instead of using the DSR encoder, we would use the phonetic encoder. And of course, that's cheating, right? Because we use the ground truth transcription, which we wouldn't have in practice during inference. But it sets sort of an oracle, right? An oracle to voicey. For the perceptual evaluations, it is based on the voice conversion challenges. We measure 2 dimensions. We measure naturalness and speaker similarity. We use crowdsourcing with Mechanical Turk, Mushra test, 120 participants, and 3 scores per utterance. So results, first in clean conditions, those are the 2 dimensions, naturalness here and similarity, and you have the Mishra scores. For phonetic, which is the oracle for here in blue on the left, which is the oracle for voicey, then you have proposed in orange, which is voicey itself, and the 3 baselines, so Stargan, pre-processing on top of AutoVC and AutoVC. And finally, the last system is the natural human recordings. And as you can see in clean condition, actually we are worse compared to the baselines, right? So we are doing worse. We believe that's because the SR is too weak. But even if we were to use the phonetic transcription, which is our oracle, we would only be able to, to perform as good as the baseline. So the baseline are actually very strong in clean conditions. But in adverse condition like reverberation here, you can see that voicey, the orange one is clearly outperforming the 3 baselines. We have a gap, of course, compared to the oracle, to phonetic, but again, phonetic uses the phonetic transcription, which we would not have in practice during inference, right? So we do have a significant gain in terms of naturalness and a slight gain in terms of speaker similarity. And reverberant plus noisy conditions, it's basically the same pictures, but the gains are less substantial. Still, we outperform the 3 baseline, and that's statistically significant, both in terms of naturalness and speaker similarity. So I'm going to play some samples just so that would be for reverberant conditions. So you get a sense. This is a source speaker. That would be the target speaker, and then the voice conversion using voicey, using the phonetic oracle, Stargan pre-processing on top of AutoVC, and finally AutoVC.
She bit her lip and looked down at her hands, which were clasped tightly in front of her.
But pray don't encourage him, as I said. She bit her lip and looked down at her hands, which were clasped tightly in front of her. She bit her lip and looked down at her hands, which were clasped tightly in front of her.
She bit her lip and looked down at her hands, which were clasped tightly in front of her.
She bit her lip and looked down at her hands, which were clasped tightly in front of her. She bit her lip and looked down at her hands, which were clasped tightly in front of her.
All right, so I guess you notice significant artifacts in the 3 baseline, while voicey seems to perform, at least in this scenario, of reverberation. So to conclude, voicey is a technique we propose. It's a new technique for zero-shot voice conversion, specifically designed for noisy and reverberant environments. We propose to use a phonetic acoustic encoder to help maintaining intelligibility, and it also uses a denoising autoencoder paradigm. And voicey was shown to outperform the baseline in both naturalness and similarity in noisy and reverberant environments. So thanks a lot. I'm done with my presentation and looking forward to the question.
Presentation. We have a couple of questions in the chat.
Sure.
Can you see them? The first one is...
Yeah, let me one sec. Yes, the first one is Javier. How different the content encoder here? Right, in the copycat voice conversion. Short answer is I don't know, Javier. I will need to check that. I can get back to you. I don't know. From EGA, which component in voicey makes it more robust compared to the baseline? Can you still? No, I need to reshare my screen. Sorry about that. The components that make it more, that make it better in reverberant and in reverberant and noisy scenarios is the introduction of those 2 modules here. So basically, those 2 modules in the bottom, so the SR encoder and the phonetic encoder. So roughly, if you look at the top of this diagram here, where you have the speaker encoder, the content encoder, and the decoder, this is very similar to the AutoVC, which you can find in evaluation. So the main advantage of voice is to introduce these phonetic and ASR encoders, which are here to maintain this intelligibility. So that's what explains the gain basically in adverse scenarios. All right, can you please help me, Tamás, with the questions?
Yeah, sure. The next one is from Simon King. If EC encodes prosody, then does the generated speech have the prosody of the source speaker?
Sorry, I need to stop sharing.
Speaker taken into account.
How is the prosody of the target speaker taken into account? We don't, from the target speakers, we just capture its speaker identity via the speaker encoder, right? So the prosody is only captured from the content encoder, and that's the prosody from the source speaker. So I'm not sure I got Simon's question, but basically that would be the answer to that question. I'll move to the next one from Mohammed. Denoising technique. Okay, I'm going to share a screen for that. And sorry, I need to switch between sharing and not sharing to see the. So I guess question from Mohammed is here, right? How do we get this clean version? Actually, I want to make it clear that during training we have 3 variants, and they are the variants of the same data. So we use the Libre speech data, which is only made of clean recordings. And then we have 2 versions which are corrupted artificially. So that means that for those 2 versions where we have reverberation and noisy or reverberation, we do have actually the clean version of that, right? So we know the matching. So that means that during training here, as input, we can feed corrupted data, but we do know what is the clean correspondence of that. And that's what we use as target during the training. Right. Okay, I think Alexi answered. Thanks, Alexi. Question from Javier, and then Cassie. If you evaluated the baseline with the reverberate speech, we did. I'm going to go back to the screen sharing mode. We did in a way, in the sense that we have this pre-pros, what I call pre-pros here, pre-pros system, which is basically we have techniques for denoising and reverberation that we apply to the corrupted audio, right, as a pre-processing. So here we have a cleaner version of that corrupted audio, which is then fed into AutoVC. So that means in the evaluation, like here, you can directly compare pre-pros with AutoVC, and well, it's not doing much better, to be honest, because it's actually the same technique, but just using some pre-processing for the reverberation and denoising. Doing slightly better here, as you can see in noisy. Probably the reverberation is not working that well, but noise removal is doing better. So that's the answer to Kasia. All right. Are there questions on sign, Tamás?
Yeah. Do we have questions here? Yes, please. Answer.
Hello, Tamás. Can you see me?
No, because I'm
okay.
Sharing.
Anyway,
but yes.
So thanks. I just wanted to clarify on like the naturalness experiments that which of the models actually use noisy data during training and which of them do not use, because for me it's unclear what part of the naturalness contribution is due to the phonetic encoder and which part is due to simply the using of the noisy training data.
Right. They have all used. They've all seen training data. In the training data, they've all seen the same material that I described, right? So those three data sets. So they have seen. That means the baseline, like AutoVC or StarGAN, they have seen corrupted data during training. So we use fair, I would say, training data set across all techniques here.
Okay, so the claim is that the naturalness improvement in the reverberant conditions is explicitly only due to the phonetic encoder that you introduced in this architecture.
That is totally correct, yes. Thanks to you.
Also, I have a last question that you mentioned that the inspiration is from the denoising autoencoder. And so that works fine when when we are adding like artificial noise to the data. But what happens if we are using like not artificially added noise, but regular noise? Does it still work?
You mean at inference time, right? That's something we have not tested. That would be our end scenario. But I don't see any reason why it would not. Probably the gains there would be a slight mismatch, right? But I guess the robustness gains would still hold. Yeah, that's I have no data to prove that, right? That's only my intuition.
Okay, thank you very much for your presentation and answers again.
Thanks, everyone.
Now we are at the end of the morning session. And because we started a little bit late, now we will have a 10 minutes break. And we will continue with the keynote at 11:15. Also, I have seen in the session that there were a lot of interactions. So I encourage everyone to continue in the spatial chat, but not during the keynote, rather after that in the morning session discussion slot. So see you there.